So I mentioned in a previous slide the concept of atomic mass unit. The fact that because we're weighing things, the atoms, that are so small that we would have to use tiny numbers if we were measuring their weight in their mass in grams or kilograms. And we chemists have come up with the concept of the atomic mass units, which is, and one atomic mass unit is defined as 1/12 of the mass of an atom of carbon-12. So an atom of carbon-12 with its 6 protons, 6 electrons, and 6 neutrons has a particular weight in a particular mass in grams or kilograms, in this case mass. So 1/12 of that mass is one atomic mass unit, and it equates to this particular number in grams. So we defined that atomic mass unit, which works out that means that carbon-12 will weigh 12 atomic mass units. And with that concept, the one atomic mass unit and being 1/12 of the mass of an atom of carbon-12, you can work out the mass of any other element you can think of with respect to carbon-12. And that's how we come up with the atomic mass scale. And it's all measuring atomic mass units, and those are the values that you get in the periodic table. Now, there is the problem that most elements exist in nature as a mixture of isotopes, and they have different abundances. So when you give the atomic mass of an atom in the periodic table, let's say chlorine, which one do you give? The one for chlorine 35 or the one for chlorine 37? When you give the mass in the atomic mass in the periodic table of oxygen, actually, which isotope of oxygen do you choose? If there are 3 naturally occurring ones, 16, 17, and 18. Well, the answer is we use a weighted average, which takes into account the isotopes that exist in the naturally occurring isotopes for that element and the relative abundance. So, for example, picking up on chlorine, chlorine has 2 naturally occurring isotopes, chlorine 35 and chlorine 37, and they have a different abundance. Chlorine 35 is around 75% of a sample, and chlorine 37 is approximately 25% of a sample of chlorine. So we use those percentages and the mass of those 2 isotopes, and we work out a weighted average for what would be the atomic mass of an atom of chlorine, which turns out to be 35.46. And that's what we put in the periodic table. Let's do a little exercise, but looking at copper. Copper has 2 naturally occurring isotopes, copper 63 and copper 65. You've got here how much they weigh, each of them, and their relative abundance. So I'm going to ask you to stop the video and work out what would be the atomic mass of copper, the one that you would find in the periodic table. So stop the video now, please. So hopefully you stop the video and try the exercise. So how would I go about it? Well, I first need to calculate the contribution of copper 63 to the atomic mass of copper. So that is what is the mass of copper 63, which is 62.93, times the abundance of copper 63, which is 69.09%. So in per 1 is 0.6909. And that is, assuming my calculator hasn't failed me, 43.47. And now I need to calculate the contribution of copper 65 to the atomic mass of copper. And I look at the relative mass for copper 65, which is 64.93. And I multiply by the abundance, not in percentage, but in per 1. So 0.3091. And that is approximately 20.06 atomic mass units. So the atomic mass of copper, of the element copper, would be 43.47 plus 20 0.06, which is approximately, depending on how many decimal places you have kept, etc., 63.53 atomic mass units.